Hello guys, so today I'm going to be showing guys how to make a simple quantum computing simulator in Python. So the first thing you want to make sure you have installed is Python onto your computer. There's many YouTube videos on this, and I'll be putting one in the description below if you need help. And then you also want to make sure you have a coding editing software on your device. Whatever you want, whatever fits you, just make sure it can handle Python. So let's get into it. So the first thing you want to do is import math. This is basically a math library that we need for this. So then def random, like that, and then we want to initialize our seed, so 1 2 3 4 5, and then true, we're gonna make our equation. So seed equals 1 1 1 1 0 3 5 1 5 2 4 5 times seed plus 1 2 3 4 5, and then we want to enumerate that just like that by 231. So then this is our linear congruential generator. So yield our seed. So we want to yield our seed times, divided by 231. Not like that, like that, sorry. And then minus 1. So then this normalizes the seed that we just made to be between the numbers of zeros and ones. So this is basically a simple random number generator. This is a very simple quantum computing simulation. So that's what that is. So then class qubit, which is a qubit, is a quantum byte. So qubit, so in our class qubit, we want to do we want 2 underscores on both sides, and then self, alpha, and then beta. So self alpha equals alpha. So this is the amplitude of the state of 0, right? So then self dot beta equals beta, which is the amplitude state of 1. So alpha equals 0, beta equals 1 pretty much. So then we want to do def underscore string underscore like that. And then we want to return our value. So f, not like that, sorry. So f alpha, like that, in brackets, we want to do self dot alpha, comma, then beta, and then self dot beta, basically like that. So then we want to make another def measure this time though, and then self. So then we're basically going to state the probability of measuring. So 0 is alpha, 2 and 1 is, stuff like that. So probability underscore 0 equals ABS, which is in quotation self alpha, 2, just like that. Okay, and then we want to make our random value equals next random, just like that. So this is basically generating a random value between the numbers of 0 and 1. So then we want to make an if statement. So if our random value is under probability 0, we want to return 0. So, and then we want to make an else statement, and then this else return 1. So basically what we're doing here is, so we're generating a value between 0 and 1 like I just said, and then here if our random value is less than the probability of 0, it measures as 0, and then else right here, and then return 1. So otherwise it measures as 1. So then we're going to make another def, and then this is basically a phase gate. So we're going to start making our gates that our equation is going to go into. So underscore gate qubit, just like that, and then squirt 2 equals math dot squirt, and then 2 inside a quotation. So this is basically, we're going to start applying our Harmon gate transformation. So new underscore alpha equals, in quotations, 1 divided by squirt 2, and then we're going to times that by qubit alpha, plus 1 divided by square root 2 times our qubit beta, just like that. So then we're gonna make a new underscore beta equals 1 divided by square root 2 times qubit alpha. This time we're going to do minus 1 divided by square root 2 and then times qubit beta, just like that. So then we're going to return these values. So return qubit into new underscore alpha, new underscore beta, just like that. So this is basically our Harvard gate transformation. So now we're going to do our phase gate. So def phase underscore gate qubit. So then we're going to new underscore alpha equals qubit dot alpha. And then new underscore beta equals -1 times qubit dot beta. And then we're going to return these values. So return qubit, new underscore alpha, and then new underscore beta, just like that. So this is basically applying our phase gate, which is another transformation, just like the one we did above. So now we're going to be testing these quantum operations. So we're basically going to be printing out what it's running through first, starting with our original numbers, and then our Harvard gate, and then our phase gate. So what we're going to do is qubit equals qubit alpha equals 1, comma, beta equals 0, just like that. So this is basically initializing a qubit in the state. So we're going to want to print out original qubit and then comma qubit, just like that. So this is basically our first numbers that we're working with. So we're going to make qubit equals Harvard gate qubit, and then print qubit after applying our gate, and then qubit. So this is basically just after running through the Harvard gate. So qubit equals phase underscore gate, and then qubit, and then print qubit after applying our phase gate qubit. So this is the end of the code. So then when you run this, you should see that our original qubit is alpha is 1, beta is 2, and then our qubit after applying the Harvard gate is alpha. So this is basically our 1 number, and then our beta, and then our qubit after applying the phase gate, which you see the alpha is the same number, but our beta is negative, the number that was above. So this is basically how you make a quantum computing simulation in Python. It's pretty simple once you get to understand the main topics and stuff. So thank you very much for watching. And if you'd like to subscribe or like the video, go ahead. I hope you guys have a good time.